So this is from the 2.2 lecture worksheets. And I just want to give this a better second look. Okay, we'll be using this and you should use it a lot. That this is basically a little cheat sheet. And this has the basically periodic table split into two halves. There's the right side of the periodic table, and these are the non-metals. So non-metals are to the right side, the upper right-hand corner. And it's also handy to have a periodic table handy and this cheat sheet. So I have a periodic table just right here, just in case I need to look at it, because you know I keep them all over the place. And this, though, is the right side, the upper right-hand corner of the periodic table, which are the nonmetals. And those nonmetals are family 5A, 6A, 7A, 8A. And look for it on your periodic. And so what you have for those family numbers is they're aligned with the charge values. And so you can write below them on your periodic table even -3, -2, -1. Okay. Family 8A does not form any ions, not typically at least. They are the noble gases. Those are the gases that are inert. They're non-reactive. That's why they're called noble gases. They're noble, they're above everything. And we'll get into the chemistry and the reasons why these are -3, -2, and -1 instead of, say, +5, +6, or +7, or any other numbers. But these are the charge. They are single atoms, so that's called monoatomic. When you have a single atom of nitrogen, it forms the 3- or -3 ion. When you have a single atom of hydrogen, it forms the -1 or just the minus ion. That's this hydride that I'm looking at there. Position in the periodic table, you can determine the charge value. Okay, and so those nonmetals form those negative charge anions with these charge values, -3, -2, and -1. Then we're going to go and review the naming. And the naming of these anions, the negative charges, are where you remove the last few letters and you replace those last few letters with this IDE name ending. And so you can see instead of this being called nitrogen, those last few letters have been taken off. Sorry, I just made that move. Let's move this back. Those last few letters have been taken off. And instead of OGEN, it's the IDE name ending has replaced it, so nitride. And so that is for all of these that are the negative charge. So instead of hydrogen, because it's hydrogen with the minus charge now, those last few letters have been taken off. And it's the last few letters, usually to the first vowel, and the ending IDE replaces that. Now, why is that? Why is the name changed? Instead of hydrogen, why is it hydride? Instead of nitrogen, it's nitride, because these are not the same as the element that's not charged. So these are the negative charge versions, the monoatomic anions, have these name endings changed to distinguish from the element, the atom that's not an ion. Okay, so on the flip side, so going down here, you have the other half of the periodic table, which is actually the majority of the periodic table, is to the left of the stair-step line. So I mentioned these last time, is that everything to the left of the stair-step line is, which are in family 1A, 2A, and 3A. Now, those are all called the A series elements. And these A series elements are predictable. You can predict the ion charge. And that's one thing. And so we already saw that you can predict the ion charge values for 5A, 6A, and 7A. So those are the A series when it has an A after the number. So 1A, 2A, and 3A, these are the A series, and you can predict the ion charge as well. So let's fill that in either on your periodic table or right here. These are +1, +2, and +3. Now you will notice here that 4A does not have any +4. And though you can predict 4A as +4 or -4, we don't need to worry about that in Chem 9. We do have some elements in 4A that are below this stair-step line. And remember, everything below the stair-step line, these are all metals. So everything to the left of this are metals, and everything to the right and above it are nonmetals. We already looked at nonmetals that are in 5, 6, and 7. And now we're looking at the metals. So the metals also includes the B series. Okay, so the B series are these 10 columns in this center section. So there are 10 columns and there are only 3 rows. There are only 3 periods in that center section, and that's called the B series. And these, you can't predict the ion charge by the family number. Okay, so for the others in the A series, one characteristic is that you could predict the ion charge using the family number. I'll add that. So 1A is +1, 2A is +2, 5A is -3. So we can't predict these using the family number. What you have for the B series are pairs. So there's chromium, there's iron, there's copper, and then there's also, this is including in part of the B series, this is tin and lead. And those are pairs in which these ions are typically formed, and you can't predict which one it's going to be. Is it going to be the +2 or the +3 for chromium? And so these, the B series, let me, that are listed here, the chromium, copper, iron, lead, and tin, those are the same pairs that are listed. These are the B series elements. Or I should say more accurately, the B series plus the lead and tin that are below the stair-step line, family 4. So that's SN and PB. Okay, so those are those pairs that we use in Chem 9. And there's also 2 that are, I'm going to highlight with green, that are not pairs. This is zinc is always +2 and silver is always +1. So this is zinc is Zn and this is silver, that's Ag. Okay, so that's what this says. Zinc always forms +2 and silver always forms +1. So you have this in 2 places. You got those pairs that are listed by the in the columns with the names, and you also have it all. Okay, and so this is the metals. The metals are the majority of the periodic table is to the left of that stair-step line. Okay, so the majority of the periodic table, most of the elements in the universe are considered metals. And so these are predicted by the family numbers, and the names are really easy. We like the names. They're basically just the original element names. So you don't have to change anything about these names. So for instance, this is lithium, the element, and it's also lithium, the ion. Okay, and I just put ion in parentheses because you can call it lithium ion or you can just call it lithium. And this is also true about hydrogen. So this is hydrogen with the positive charge. And this, when it has the positive charge, it is called hydrogen, or it is referred to as the hydrogen ion. Now I want to point out that this is different from the hydride, zooming in here, when you have hydrogen, that's the negative ion. So the negative ion has the IDE name ending, but the positive ion does not change the name ending. So zooming back out. Okay, so this is, the names are, you don't change any of the names when you have a positive charge. Great. The only complication of these metals are the ones that have more than one charge. Those are the B series. Okay, and for those in the B series, these guys in the center section +2 over on the right, for these you use the Roman number to indicate the charge value. So that's why this is chromium, which is the element Cr. Well, when it's the +2 or 2+ ion, it has the Roman number 2. Okay, so we looked at that last time. So I just wanted to review all this so you can really get a good look at what all this is. So use these sheets, use your periodic table, mark up your periodic table, and you can use all of this during a quiz you saw. Okay, so let's go to this lecture worksheet. And we have the ionic compound chemical formulas. Oh, hold on a second. No, the one I wanted to go back to. Okay, so this is what I had reviewed in the last lecture is I went over those charge values. Okay, so the charge values for the elements that are in the A series, family numbers. Okay, so this we had done down here, and also wanted to point out that reviewing writing the names. When you have the names of the metals, those are the positive charge cations. If you have a cat and you think positively about cats, that's great, that works out. Those are the positive charge when it's called a cation. Okay, for the positive charge cation, you just use the name of the element to name the ion. For the negative charge, the nonmetals, those are the negative charge anions. Well, that's where you start with the element name and you remove the last few letters and you add that IDE ending. Okay, so when you have calcium, calcium is a +2 ion because it's in family 2A. And so that is the name of the ion is the same as the name of the element, calcium. Or aluminum, which is in family 3A. And so you would quickly look on your periodic table for that element symbol Al, find it in family 3A. And so you have that aluminum is the 3+ ion. And so the name of that ion is just called aluminum, the same as the element. And then when you have the nonmetals, you element name, and then you take off that IDE ending. So for this example, phosphorus. Phosphorus is the element symbol for P, and it is in family 5A. So because it's in family 5A, those are the ones that form -3 ions. So this is written as phosphorus element symbol P with the 3-. And so you take off to write the name of this element. To write the name of the ion, you start with the name of the element, which is phosphorus, and then you take off the last few letters, usually to the first or second vowel. And then you add the IDE ending. So this is phosphide. So if you're sitting there wondering, well, how do I know? How many letters do I take off? Well, you always have, going back to here, this as a reference. How many letters to take off is usually to the first or second vowel. And so that's what this says here. Take off the last few letters to the first or the second vowel. Well, you always have these are the names of the anions. Okay, so those are the anion names that you can check. And so going back to here, the name of that ion of the P-3 ion. So for this element, chlorine. So chlorine has the element name chlorine. The element symbol is Cl, and it's in family 7A. So chlorine is in family 7A. So all of those elements in 7A form a -1 ion. So that's why it's written Cl-. And then when you're trying to figure out the name of that ion, you take off the last few letters. So on the right, move into the first vowel, and then adding the IDE ending. So it's why sodium chloride, that's table salt, is called sodium chloride and not sodium chlorine. So that when you are talking about table salt, I'll write that here. For example, table salt is NaCl. That's the elements as the chemical formula. Okay, so the chemical formula puts those ions together, and we'll get to that. Well, the name is sodium chloride. So that's the chemical name. And it is called sodium chloride, you notice, with the IDE name ending. Okay, and it's sodium chloride, not sodium chlorine, even though Cl in the periodic table, the element is called chlorine, but the "ide" means that this is the chlorine ion, Cl minus. And so that's together with the sodium ion, Na plus, and this is an example of an ionic compound. And so we're going to get to that next. Okay, so we had gone over these names of those ions with those charges last time, but this was going back to review how exactly those names come about. And also the goal was to really dive into and look at everything you have on this page. Okay, so use this as a reference page. There's nothing you have to fill out on this except for to use it, mark it, use it so that you understand. We are going to get back to this section, which is the common polyatomic ions, very soon. Okay, so first, today's lecture worksheet. So this is now, we're in 2.3 lecture worksheets. And now we're putting it together. The monoatomic ions, so those are cations and anions, those come together. So you need the charge values. You're going to use the periodic table for those charge values, the family number, and you are going to put those together to form the ionic compound. And as I mentioned, the ionic compound is neutral. It is no overall charge. And so what happens in this process called the crossover rule is the crossover rule allows you to put together the ions with the correct charges or the correct ratio so that the charges will cancel out so that there's no overall charge. So it's really easy to see that if you have one sodium ion that's a +1 charge, you will need one chlorine ion that's a -1 charge. So that's a 1-to-1 ratio. But this is easy for a 1-to-1 ratio. It's not as easy when you have the charge values that are +2 or +3, or when you're combining +2 and +3. So this is why we have this process called the crossover rule. So in the crossover rule, the purpose is to determine and write the chemical formula. Now, I want to point out that these are called chemical formulas, and the formula shows there and how many. And that how many is as a subscript. So that is a small lowered number. Okay, so an example is H2O. So the subscript is that 2. That 2 is a small lowered number. Now this is different from these, which are superscripts. So the superscript is written as a charge value with a plus or minus. So it's a plus or minus charge value. That's a superscript. And so the idea that a subscript is a small raised number compared to a subscript that is a small lowered number. And so the chemical formula only shows subscripts compared to the ions that only show superscripts. Okay, so you start with the crossover rule starts with superscripts. Those are the charge values. And then what crosses over and down, these cross over and down to become subscripts. Okay, question in the chat asking me what would this look like as a molecule? It would look like this. So if you have NaCl, this is Na plus and Cl minus, you have one of those and one of those. And if you have Li2, subscript 2 with an O, what that means is that you have 2 lithiums, so 2 of these that are the lithium ion plus charge. And then one of these that is the oxygen -2 ion. And those are all clustered together. And so that is the correct ratio. You have no overall charge. And so why does that work is because you have +2 or 2 times the +1 of the lithium and then 1 of the -2 ion. And so this has no overall charge. because you have enough charge values that are positive, values that are negative. And so that's the goal of the crossover rule. So we don't have to draw these pictures. So the crossover rule starts with the anion and cation with charge values as superscripts, okay? So you use the family number for aluminum, which is 3A. So in family 3A, that forms the charge value plus 3, okay? So I would write this, I'm going to do this right here. So family 3A, this is right, the aluminum element symbol. And then you're going to want to write the plus 3, or I'm going to write it 3 plus. Plus 3 or 3 plus, doesn't matter, as long as it's a superscript and also has that correct element symbol. So then that's the cation. So that's the positive charge. The positive charge is always first. Okay, so I'm going to write that first. First, number one. Second is the anion. The negative charge always follows. Positive leads, negative follows. So the anion is next, and the anion is the negative charge. And you want to write that with the charge value as a superscript. How do you find that charge value? You use the family number. You use your periodic table. So this is O, that is oxygen, that is in family 6A. So family 6A, those form the -2 ions. So you want to write next to it. So next and next to it, you want to write the element symbol O, and then the charge value as a superscript. Family 6A forms the 2 minus or -2 ions. Okay, so you have those element symbols and the charge values. Now is when you involve the cross over and down process. So what crosses over and down are only the number values. Just the number values cross over and down. So I'm going to circle this 3 and crossing over to the other element and down to become a subscript. Okay, so you will have then, I'm going to write this as AL, and then a 2 over here. Okay, and there's an O here also. So the other number, which I'm going to circle in purple, is a 2. Okay, so notice I didn't take the minus. I'm going to just take the number, and that crosses over and down. Now this has to cross back in order to go over. So this has to go back to become a subscript for the aluminum. So this becomes a 3 here, and it's a 2 here, and it's no longer a 2. So actually, let me show you that process. This 3, when it crossed over and down to here, boy, I better get that right. Sorry, that 3 crossed over and not a 2. Let me fix that. So that's a 3. That's a 3 that was here, and it crossed over to here. So when it crosses over and down, it's no longer up there. Okay, so that's AL, and what crossed over and down was this 2 that was here, and it's a 2 there. So it's AL2 and O3. Phew, got that one right. Okay, thank you to everyone who was about to help me fix that. All right, so let's take a look at this process. So this is going to use the crossover rule. And so what this is this is the correct ratio of aluminum ions to oxygen ions so that you have no overall charge. And so this has 2, let me write this out here. This has 2 aluminum plus 3 ions. And so if you have 2 ions at a plus 3 charge, that's going to add up to plus 6 worth of charge. And there are also in this compound 3 oxygen -2 ions. So oxygen is the -2. If there's 3 of them, that's going to add up to the charge. Putting all of those charges together, the plus 3 and -2, -2, -2, that gives you no overall charge. And this is a neutral compound. So this is a neutral ionic compound, and that's the goal. That's why ions come together, is that ions have these charges, and what makes them stable and exist in the world is by pairing up with other charges so that everything is neutral and has no overall charge. Okay, so opposites attract naturally in physics, and they can cancel out, and that neutralization is what drives an ionic compound. Okay, so first, here's these examples. So we're going to use the crossover rule to write the chemical formulas. So these are the chemical formulas that show what elements and how many as subscripts. but we're starting out with the charge values that are superscripts. And where are we getting those charge values from? So have your periodic table handy. Okay, so you have calcium that is in, that's calcium, the element symbol Ca. So that is in family 2A. I'll write it right below the name. And then bromine, that's Br, but the IDE ending should tip you off. It means it's the anion when it's the IDE ending. So bromine is the original element. And so bromine is in family 7A. Okay, so what are the charge values for family 2A? This is a +2 or 2+ charge value for calcium. For bromine or bromide, this is in family 7A, those form -1 ions. So you can put a 1 there, or you can put 1-, or you can just put a negative charge. I'm going to put 1- for the charge value, and then show you what you're going to do with that 1. So this is the crossover. What crosses over is this 2 has to come over and down and become a 2 here. So this gets crossed out. This 1 crosses over and down and becomes a 1 down here. So that gets crossed out. So what you're left with is you don't have any more plus or minus signs once these cross over and down. So what you're left with is Ca1 and then Br2. Now with the 1 subscript, you can get rid of the 1 subscript. You can get rid of any 1s, in fact. So if there's a 1 multiplied by a number like 1 times 5, you can get rid of that 1. It is just meaning here for this 1 subscript, there's 1 of these calcium ions. Well, just having the element symbol is good enough. You don't need the 1. So you would actually correctly write this just CaBr2. And you want to correctly get rid of that 1 because it's redundant to have the element symbol and a 1. Okay, so that would be the chemical formula. Next one, you've got sodium and sulfide. So sodium is the element symbol Na, and we'll find on your periodic table in family 1A. Okay, so sodium in family 1A, all of those form a 1+ ion. So you can write just the plus, or you can write 1+, or you can write +1. I'm going to write the 1+ and show you what happens to that 1. Then sulfide, well, the IDE name, and it is an anion. So this is the IDE name ending here, just as it was here. It's an anion, it's a negative charge. So when you're looking for it, you're not going to find sulfide on the periodic table. You will find sulfur, which is in family 6A. So that's sulfur, that's an S, and you want to have that sulfur is in family 6A, and those form -2 or 2- ions. So it's the numbers that cross over and down. So this 1 for this Na crosses over and down to become a subscript 1 outside of the sulfur. This 2 crosses over and down and becomes a 2 outside of the sodium. At the same time, you get rid of the plus and minus signs. So this becomes Na with no plus charge, but a subscript 2. And this is S with no minus sign, but a subscript 1. So remember, you can get rid of 1s. So this is more correctly written as Na2 and then S. Okay, so I'm going to underline the correct version. So why can you get rid of the 1s? It's because having the 1 and the element symbol S is redundant. You only need to have the element symbol. Okay, let's look at the next one, which is calcium and oxide. So when you have calcium, this is the element symbol Cl, and we had seen that before from family 2A, it forms a 2+ ion. For this one, it is oxide. The IDE ending should tip you off, and you think, okay, that means it's a negative charge anion. It's over on the right side of the periodic table. Those anions are nonmetals. So that's oxygen in family 6A. So that's the element symbol O. And in family 6A, these are 2- ions. Okay, so what's going to cross over and down is this 2 is going to be a 2 outside of the oxygen symbol. So it's no longer up there. This 2 crosses over and down and becomes a 2 outside of the calcium. So it's no longer up there. So now what you have is you have the calcium, no plus sign, but there's a subscript 2. You have the oxygen, no minus sign, but there's a subscript 2. Okay. So now when you have this has the same ratio, 2 to 2, well, you can divide. When you can divide both by a common denominator, you can divide both of these by 2, well, then this becomes Ca1 and O1. You can divide both of those by 2, both subscripts by 2. And remember, you can get rid of any ones. So this becomes Ca and O. And that would be the correct chemical formula for the calcium with the oxide. Okay, how do you guys feel about this? Can I get some thumbs up? I got 1. Okay, good. Thanks, James. So let's take a look at this one, which is iron 2. Now, when you have the Roman number, remember the Roman number means that's the charge value. So this is iron, that's the element symbol Fe. And this Roman number is the charge value that is +2. Okay, so you're really gonna like those Roman numbers when you get used to seeing them. So that's +2 or 2+. When you find this nitrate, so nitrate is not the IDE ending. See, not bromide, IDE, sulfide, oxide. What is it? What is the ATE ending? So the ATE ending is one of those polyatomic ions. So the polyatomic ions are going back to that page. Let me go back to that page, which is here. Those polyatomic ions. Is there a question, Skylar?
Yes, I do have a question.
Yes.
So can you explain why you can divide by a common denominator?
Okay, so let's go back to here. So this is the examples that I have so far are CaBr2 was correct. Oops, don't want the erase. CaBr2 was correct. The subscripts are 1 and 2. There's no common denominator there. Na2S was correct. I didn't do any dividing there because the subscripts are 2 and 1. But this Ca2O2, the subscripts are 2 and 2. So what that means is that there are 2 calciums to 2 oxygens. 2 and 2 is something that you can divide both of those by the same one number, 2. You can divide 2 by 2 and get 1. You can divide 2 by 2 and get 1. And saying this a different way, a ratio of 2 to 2 is the same thing as a ratio of 1 to 1. So let's say the numbers were 3 and 3. So 3 and 3, a ratio of 3 and 3 can also go down to a ratio of 1 and 1. Or if you have a ratio of 4 and 2, that can go down to a ratio of 2 to 1. That would be an example of dividing by a common denominator.
Okay, so you almost want to have like the
lowest,
the smallest.
Yes.
Okay, gotcha. Yes. Thank you so much.
You're welcome.
Sort of like in math, when in general, they just want you to like reduce or simplify your final answer.
Exactly.
What
exactly.
we're doing. Okay.
Exactly. They want you to do that. And it standardizes that final answer. Exactly. Thank you. Okay, so now let's go back to the quick look at this is the common polyatomic ions. So on the video, I had mentioned these common polyatomic ions have the name endings that you want to pay attention to, is that for the most part, these name endings are ATE or ITE. And what these are, underlining all of these, ATE, ITE, underlining all of those, ATE or ITE means that it's a polyatomic where there are more than one ion, more than one atoms in the ion. So more than one type of atom. What you have is ATE and ITE means that you have whatever atom plus an oxygen. So for the name nitrogen or nitrate, for the name nitrate, You can see the beginning part of the name is almost like nitrogen. It's NITR. And so nitrate means you have a nitrogen and some oxygen in there. Exactly how many is the chemical formula, NO3 minus, okay? Or nitrite, it has the beginning part of the name nitrogen, and the ITE ending means there's some oxygen in there. And so nitrate and nitrite are very similar. The ATE ending has one more oxygen than the ITE ending. So that's NO3 for nitrate, and NO2 has one less for nitrite. Okay, and so here's another example is sulfate, which has the beginning part of the name is sulfur, and the ending part is ATE. The ATE means there's an oxygen in there. How many is going to come from the chemical formula? So sulfate is sulfur and oxygen. There's one sulfur and 4 oxygens, and the whole thing has a -2 charge. But there's also sulfite, which is also the ITE ending, means there's but one less. And so this is the chemical formula instead of SO4. And the charge value doesn't change. It's still -2 charge. And you can see the same was true about nitrate and nitrite. This was NO3. This was NO2. The difference is just the number of oxygens, but the charge value is the same, -1. Okay, so use this. This is actually one of the things that you will want to look at a lot. You will need this because this is not on the periodic table, but you're going to need it just like you need the periodic table. Okay, so I'm going to keep this handy. Hopefully you keep it handy. Actually, I have a paper version next to my periodic table. And I need that because I was working with this, trying to write the name of iron 2 with nitrate. So nitrate is a polyatomic ion. And I recognize that it's a polyatomic ion because it has that ITE ending. It's not nitrogen, it's not nitride. From the ATE ending, I know that there's more than one atom in there. And so this is the polyatomic ion. You want to write in parentheses, NO3. All of those atoms are bonded together, and there's a negative charge applied to all of those, the whole thing, okay? And so the parentheses is important because when you take a number and you cross it over and down, it has to not go inside the parentheses. It has to go outside of the parentheses. And so it crosses over and down to outside of the parentheses. See this green barrier, and it's no longer up there. This no number I'm circling nothing here, and I'm crossing nothing over and down. That's okay, because what you're going to end up with is Fe with now no positive, because the 2 is gone, and that means positive's gone, and no number there, nothing crossed over and down. But in parentheses next to it is NO3, and there's a 2 outside of it, and that's that chemical formula there. Okay, now what do you do with that 2? Do you multiply it into the parentheses? No. The parentheses are really like a barrier. Nothing goes inside of it, nothing comes outside of it. Do not multiply it in. You can't divide, you can't do any common denominator, you can't reduce, and that is it. That's the chemical formula right there. So for the next one, you've got lead 2. So that Roman number 2, remember, is the charge value. Okay, so that means you need the element symbol for lead, which is Pb, and the charge value is 2+. And then it's with the same polyatomic ion, the nitrate that we used previously. So I'm going to write that chemical formula in parentheses, NO3, and then the minus charge. Okay, so this is going to be, the 2 is going to cross over and down and become a 2 outside of the parentheses. So remember that parentheses is like a barrier, and you get rid of that 2. No number is attached to that negative, and that no number crosses over and down. So what that means is now you have Pb with no number, positive charge, and then you have in parentheses NO3 with a 2 outside as a subscript. And then that's it. You don't have to divide anything. You don't have to multiply anything in. For this next one, you've got ammonium. So ammonium, you are not going to find ammonium on the periodic table. This is a polyatomic ion. And the same is true about sulfate. What should tip you off about the sulfate? Should be that ATE ending. It means that a polyatomic ion is when you have more than one atom bonded together, and ATE means that there's oxygen stuck to something else. List and look for ammonium and sulfate. Okay, so this you will find on your polyatomic ions list. Ammonium is parentheses NH4, parentheses around the whole thing, and a positive charge. And then sulfate, you want to also write that in parentheses. So this is SO4 and then a 2- charge. So the parentheses are becoming super important, especially here, so we know where to cross things over and down. So first of all, this is just a positive. So there's no number to cross over and down. So I'm circling nothing and I'm crossing nothing over and down, just putting the arrow there. Okay. But this has a, so this, I'm going to write the NH4 in parentheses to start with, NH4. Okay. So now there's no positive charge. This next is SO4 with a 2. So that 2, I'm going to cross over and down, and it becomes a 2 outside of the NH4 parentheses. So I'm going to add outside of this NH4 parentheses a 2. Okay. And then what happened is that the next is still the SO4, keep it in parentheses, does not have anything over here. So I crossed nothing over and down, and so there's nothing outside the parentheses. So when there's nothing outside of the parentheses, when there's no subscript outside of the parentheses, I need to write this so that I can fit it in. You can get rid of the parentheses. So this is going to be similar to the idea of simplifying. The simplest version of this would be NH4 with the subscript 2, and then no parentheses, just SO4. Because the parentheses are redundant, you need the parentheses when there's more than one of them, when there's a 2 outside, such as the previous examples, or in this one, the 2 outside of that parentheses. You need that parentheses. But when you don't have any subscript outside of it, you don't need the parentheses, so you get rid of them. Okay, so this would be the correct chemical formula. And then let's get to this last example, and then I'll take questions, and then we'll take our break. The last example is calcium. So calcium we used before is in family 2A. So this is calcium, the element symbol Ca, and that has a 2+ charge. Sulfate. So when you see that name sulfate, you should notice that ATE ending. ATE ending means it's a polyatomic ion. There's oxygen stuck to something else. So this is the elements, the chemical formula in parentheses for the polyatomic ion is SO4 and then 2-. Okay, so you've got a 2 that's going to cross over and down outside of the parentheses. So it's going to be a 2 over here. And then you also have this 2 that's going to cross over and down outside of this calcium symbol. It's going to be a 2 there. So we can get rid of that too. So what do you have left? You have the calcium Ca with no +2. And it has a subscript 2 now that came from the sulfate. SO4 with a 2 outside the parentheses. Okay, so here's a few steps you can clean this up. So you can divide both of these by 2. That's the reducing to common denominator. So this is going to be Ca1 and then in parentheses SO4 1. Okay, well, you can get rid of any 1s because 1s are redundant. So this just becomes Ca and then in parentheses SO4. Well, this is another one. When you have a parentheses, you can get rid of when you have a parentheses that doesn't have a subscript outside of it. You'll notice this parentheses has a subscript inside of it. That 4 is there. Well, that's different from a subscript outside of it. So inside of it, don't look. But outside, you can, if there's no subscript outside the parentheses, you can get rid of this parentheses. Why? Because you don't need it. You only need the parentheses when there's something outside of it. So this is going to be Ca and SO4 would be the correct chemical formula. So that combines all those little extra steps. It is going to be easier. So this is, we are using Greek prefixes. Those are Greek prefixes in the name, and those just directly translate to the subscripts that mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. So those Greek prefixes in the name directly translate to subscripts in the chemical formula. There's just a few other things you need. This is the mnemonic I mentioned, mother eats peanut butter. This is 1 carbon. So this is 1 carbon, which is methane, that's CH4. This is 2 carbons, that's the E in eats, that's ethane, that's C2H6. Peanut butter, that's 3. So that's the 3 in C3H8. And that's the name propane, starts with a P. And then butter is the B, that's butane, which is 4th. And so that's the chemical formula C4H10. So when you know the number of carbons is N. And to calculate the number of hydrogens comes next. You actually take that N and you multiply it by 2 and you add 2. So for instance, for methane, this is the first, so that's 1 carbon. That 1 carbon means that you have C1 and then H, which is going to be 2 times 1 plus 2. So this is C1H4, or to shorten it or reduce it, you can get rid of the 1 and it's just CH4. So that's how you get that chemical formula for methane. It's the number of carbons, which is the first subscript, and then you multiply that number times 2 and you add 2. Okay, so let me show you how that works for the second carbon. So this is the second in the series is ethane. So ethane is so C2, and then you want to have the hydrogens is going to be 2 times 2 plus 2. So that's C2, or 2 times 2 is 4 plus 2 is 6, C2H6. So that's how you get that chemical formula. So this is the general format for figuring the chemical formula or the number of hydrogens in a hydrocarbon. That's called a hydrocarbon. It has only carbons and hydrogens and all single bonds. Okay. Which were the water. The water is H2O, not dihydrogen monoxide. Ammonia is NH3, not trihydride. And ozone is O3, not trioxide. So basically, when you are writing the chemical formula, you're going to take the name, basically the Greek prefixes, and turn them into subscripts, except for some of these which have the common names, which are the hydrocarbons, and these few traditional names. So you are having one last bit, which is kind of similar to the ionic compounds, is that even though these are not ions, for the second element, you take off the last few letters of the name and you replace with an IDE ending. And this is even though it's not an anion. This is basically a rule that is for all compounds that have 2 elements in them. They're called binary compounds, that whether it's an ionic compound or covalent compound, when there are 2 types of elements in there, it's called a binary compound, and you take off the last few letters and replace with IDE. So we'll do that in this one too. So this is writing the element names when you're given the chemical formula. So this is 1 carbon. So 1 carbon means you just write the name carbon and you indicate how many using a Greek prefix, but only if there's more than 1. So when you have only 1, you don't need a Greek prefix. So no mono for when it's the first atom. Okay, so you don't use mono when it's the first atom. So you just jump right into the element name, which is carbon. For the second element, the name is oxygen. Okay, so now not oxygen, but you want to take the last few letters and replace it with the IDE. That 2, that subscript 2 means you need a Greek prefix. to indicate how many. And there's 2 of those. And so that's carbon and dioxide. That's how CO2, carbon dioxide, got its name. This next example is CO. So this again is 1 carbon. So you don't start with mono if there's 1 for the first element. For the second element though, which is oxygen, so I'm going to write oxide for that. Okay, so not oxygen, but oxide, because you have that IDE name ending. This is 1 of those oxygens, so I would write mono. For the second element, you do indicate how many of the second atom using a Greek prefix, including if there's 1. Okay, so this is how carbon monoxide, and I can combine those vowels to write just carbon monoxide instead of carbon monoxide, and that's how carbon monoxide got its name. So for this example, you have P2O10. So this is 2 of the first element. So 2 of the first elements means you start with the prefix di, and then the name of the element is phosphorus. So diphosphorus. And then there's 10 of the next element. The next element is oxide. Okay, so it's oxygen, but you want to take off those letters and add the IDE. And to have 10, the prefix for 10 is deca. So this is diphosphorus decaoxide, P2O10. The next one is SO2. So you have the first element is the sulfur. And for the first element, when there's only 1 of those, you just jump right into the element name, not monosulfur, but sulfur. And then the second element, there's 2 of. The second element is again oxygen. So this is going to be oxide, not oxygen. And to indicate the 2 of those, you want to add the prefix dioxide. So that's sulfur dioxide. That's the air pollutant we talked about last time. Br2O7. So this is Br, which is bromine. Now, because there's 2 of those bromines, you want to start with the Greek prefix indicating 2, which is di. Okay, and so this is going to be di, and the element name is bromine. Then the next element is oxygen. So that is going to be oxide in the name. And you need the Greek prefix indicating 7 of those. So the Greek prefix for 7 is hepta. So dibromine heptaoxide. So notice it's dibromine, not dibromide, because it's bromine, the element, and the IDE ending is for the second element only. Okay. Now you've got C2H6. Don't start calling this, don't start thinking you're going to go down the road of dicarbon hexahydride. Why not? Because anytime you have only carbons and hydrogens, it is a hydrocarbon. It's one of these with those common hydrocarbon names. So C2H6 is this one that's ethane. So let me scroll down and write that. C2H6 is the common name for the hydrocarbon ethane. Okay, so it has the A and E name ending. That's a hydrocarbon. That's what the second hydrocarbon in the family. Okay, so anytime you see only carbon and hydrogen, you're going to use one of those common names, and those end in A and E. So here's the next one, CH4. That's only carbon and hydrogen. So don't be calling it carbon tetrahydride. It's not. Okay, so anytime you're going down that road, stop yourself. It's one of those hydrocarbons. It's the first in the family with 1 carbon, and it's called methane. So it ends in A and E, and it has the 1 carbon. Mother eats peanut butter. M is first with meth. How about O2? O2 is only a single element. Okay, so when you have 1 element, now you're not talking about a compound anymore. So this is the element oxygen. It is oxygen that is a diatomic. It's a molecular element, and it does not have any other name. Okay, it's not called dioxide. Okay, because these are names that are only when you have compounds, when you have more than 1 element. So let me highlight that again. This is covalent compounds, or when you have more than 1 element bonded together, 2 different elements like sulfur and oxygen, or hydrogen and oxygen. But when you have only 1 element, like this example, oxygen, It's O2. Yes, though there are 2 oxygen atoms bonded together, it's just one element. Okay. And then finally O3. So O3 again is just one element. This is that special name, ozone. And you'll notice there's one last video, which is the indoor air pollutants, which I'll get to. I'll post it and we can watch it together. But I know since I'm going to finish this worksheet and it'll be time to go, I will also send you off and you can watch it with me or just take it and watch it later. This is writing and balancing chemical equations. And the goal is to make sure the chemical reaction has been written so that it obeys the conservation of mass with equal numbers of atoms on both sides. And so the process begins with writing chemical formulas. So that's why we went through all this before, is how to write the chemical formulas, because they go into chemical reactions that we can then do those reactions, whether it's a combustion reaction or something that's changing colors or having bubbles. That's fun to see, but we have to go through the process first of understanding what we're seeing, writing those chemical reactions and balancing them to become equations. So you're writing chemical formulas for those compounds, and those are all those nomenclature rules we've gone over in the last 2 lectures. They're mostly going to be ionic compounds, but these on this example are mostly covalent compounds. So you want to make sure that you are paying attention to anything that might be a diatomic molecule that are not compounds, like hydrogen is H2 and nitrogen is N2 and oxygen is O2. When you see the word hydrogen, it doesn't mean it's just the symbol hydrogen. Hydrogen, nitrogen, and oxygen are always present in nature as diatomic. These are called those molecular elements. They're always molecules, and it is a molecule of 2 atoms bonded together. Okay, so the process will involve taking an inventory. Basically, you're counting the atoms on one side and making sure they're equal to the atoms on the other side. And the way you are making them equal is by adding a number in the front of a compound or an element, which is called a coefficient. Now, the coefficient has to be a whole number value. Can't be a half, can't be a fraction. It has to be a whole number value. And this is a tip, is to start by converting an odd number into an even number. In math, you can turn an odd number into an even number, like 1 times 2 can be an even number too. You can never, ever, ever turn an even number into an odd number. Okay, so you can only convert odd numbers into even numbers. And one very important thing is don't change any subscripts. Even though you want to change subscripts, the only way you can balance atoms is by adding coefficients. That's the number at the front. So it has to be a number at the front. It should never be any subscripts. Okay, and so writing the complete balanced equation, it's going to start with converting these names into chemical formulas. So carbon is just the element symbol C, and is a plus sign. And when you see oxygen gas is the element symbol O, but oxygen is one of those molecular elements that there's 2 of. Okay. Now you could add a subscript to indicate that this is a gas. It would look like this. And that's only because gas is in the word equation. So I put a G indicating a gas in parentheses. Reactive form is going to be an arrow. Okay, so reactive form, the words are an arrow separating the reactant side, that's the left side, from the product side, that's the right side. This carbon dioxide is the compound. That's the chemical name of a covalent compound. And how do I know it's a covalent compound? Because of this prefix di. Remember those Greek prefixes, di, mono, tri, tetra. That means it's a covalent compound. And if it's a covalent compound, all you have to do is take the names of those elements that you see, like carbon, and indicate how many of them using the Greek prefix. So this is, the next one is dioxide, so that's CO2. So there's 2 of the oxygens. Okay, so then you want to balance this. Well, guess what? There's 1 carbon on both sides. Oops, I want to use this color. There's 1 carbon on both sides, and there's 2 oxygens on both sides, so this is balanced. No need to change anything or add any coefficients. But we'll see for the next one. This is carbon, which is the C, and oxygen gas, that's O2 and G again. Okay, react to form, that's an arrow. Well, this time it's carbon monoxide. So this is another one of those where I know it's a covalent compound. And because it's a covalent compound, there's no crossover rule. There's no charge values. This is take the element name and turn it into symbols using the Greek prefix. So the Greek prefix mono means there's one oxygen with that one carbon. Now this time there is one carbon on both sides, but there's two oxygens on this side. So in order to balance this, there's two oxygens on this side. I need to take the side that is the even number, which has only one oxygen, and put a 2 coefficient. So now I've got 2 carbons on this side because that 2 multiplies into this whole compound. And there are also 2 oxygens. So the 2 oxygens balance, but now I need to balance this. So there's 2 carbons on this side. So I'm going to put a 2 coefficient in front of that carbon. So that means that there's 2 carbons on this side now when I add that 2 coefficient. So there's 2 carbons on both sides and there's 2 oxygens on both sides. And now this is balanced. Okay. For the next one, I've got nitrogen gas. So nitrogen gas is one of those that is not just the element symbol N, but it is N2. Okay. And you could put G in parentheses for the gas. Okay, because it's indicated in the name. And is a plus sign. Oxygen gas, that's the O2 again. So not just O, but O2 and a G in parentheses. Reactive form is an arrow. And then they gave us the name and in parentheses, they gave us the chemical formula, nitric oxide. So that's NO. So this is the chemical formulas and it is not balanced. I can see that there are 2 nitrogens on the left side, and there are 2 oxygens on the left side. Well, in order to balance this, I'm going to need to add a 2 coefficient in front of NO, and that will now give you 2 nitrogens. This multiplies through to both of those elements and 2 oxygens. So though the coefficient is in front of N, it applies to both of those elements in the compound. So now this is balanced. There's 2 oxygens on both sides, 2 nitrogens on both sides. So this is balanced. Okay, so scrolling down here, I've got hydrogen gas and nitric oxide. So hydrogen gas, is H, but it's diatomic, it's H2. Okay, hydrogen is always one of those molecular elements. It's a gas, you want to put G. And then and. So nitric oxide, that's the one that we just used up there. So I can use that again, NO. Okay, so this reacts to form. And water. So water is the name, but the chemical formula for water is H subscript 2 and O. Then you have an and, a plus sign, and nitrogen gas. So you want to write nitrogen element symbol N with a 2. Nitrogen is another one of those that's always diatomic. There's always 2 of them. Okay, so we can see that this is not balanced, that there are, looking at this one, there's 2 nitrogens on this side, and there's only 1 nitrogen in NO on the left. So I'm going to start by putting a 2 in front of this NO. That's because this is an odd number having only 1 oxygen there. And so that's an odd number having only 1 nitrogen there. So now there's 2 nitrogens and that will balance that. But what this also does is it causes me to have the 2 multiplies through to the oxygen, and there are also 2 oxygens. So there are 2 oxygens on this side now, and I need 2 oxygens on this side. There's only 1 oxygen in H2O, so that H2O needs a 2 in front of it. So this will now have 2 oxygens with that 2 coefficient. And the other thing it affects is that H2. So there's going to be 4 or 2 times the subscript 2 of the hydrogens. There are 4 hydrogens, 2 times H2. Okay. So that means I need 4 hydrogens on this side. So I'm going to have to add a 2 coefficient in front of here so that I will have 4 hydrogens now with that 2 times H2. So let's check. There's 4 hydrogens on both sides. There's 2 nitrogens on both sides, and there's 2 oxygens on both sides. So this is now balanced. Okay. And then the last one is this aluminum and chlorine gas. So aluminum is the element symbol Al. So aluminum is not diatomic, so don't put any 2 there, but it is a metal. So, and chlorine gas, they gave us this, which is, it's not just chlorine, but Cl2. And chlorine gas is a diatomic, and it's a nonmetal. So this reactive form is an arrow. And this gives us solid aluminum chloride. Now you'll notice a couple things. They gave us the word solid, and also that it's aluminum and chloride. Notice that IDE name ending. So aluminum and chloride is a metal and a nonmetal. Metal and a nonmetal bonded together with an IDE ending. This means it's an ionic compound. For an ionic compound, then that kicks in. You have to write the ions as charge values and use the crossover rule. So everything above that, we didn't have any of those because those were covalent compounds. But once you have an ionic compound, this kicks in. So writing the ion of aluminum is in family 3A. So that's in family 3A, so that's 3+. And then chlorine, that's Cl, and that's in family 7A. Family 7A is -1. So using the crossover rule is this 3 crosses over and down, and this nothing crosses over and down. So the chemical formula you're going to have on the product side is not AlCl2. So don't write AlCl2, don't just slap those 2 together. But you have the crossover rule providing that this is Al and Cl3. So this 3 crossed over and down, and no number crossed over and down. So that's how you have AlCl3. It's an ionic compound. That's why you had to do that. So there's a little tip off there that you had this aluminum chloride, the metal plus nonmetal. Now I still need to balance this. So this is the odd number 3 to the even number 2 chlorines. So I'm going to put a 2 in front of this side on the right side, 2 AlCl3. So that'll give me 2 aluminums and now 2 times 3 or 6 chlorines. So that means I'm going to go back here and put a 3 in front of Cl2. That'll be 6 chlorines, 3 times 2. And then I'm going to add a 2 in front of Al. So that's 2 aluminums on both sides and 6 chlorines on both sides. And so now that's balanced.